Hi everybody, welcome to the 2020 APAC Groundbreakers virtual tour by APAC OUC. Want to mute? There we go. Sorry for that. So welcome to the 2020 APAC Groundbreakers virtual tour by the APAC OUC. This year, our event is even bigger than ever before. We've got 174 sessions, and this includes normal sessions, workshops, hands-on labs, from over 123 different speakers, and it covers 11 days. So we're now in the second week of this, which is really exciting. Also, it will cover sessions in 4 different languages. Now, please remember to register to as many of these sessions as you can. All of these sessions will be available for replay for the next 2 weeks after the sessions are finished. So for 2 weeks, you can go online and you can review these sessions and watch various different sessions because they're all being recorded for you. You can also interact with the speaker at any time during these 2 weeks by posting questions and comments directly in the playback session page. Just go to the next. There we go. Now, this wouldn't be possible without our sponsors. So we first want to thank the Oracle user groups and the Java user group that made this event possible, but also our sponsors, the Oracle Groundbreakers and CloudDB. Now, for today's session, build a container platform with alternative tools by Michel Schildmeijer. Please feel free to write questions at any time during the session in the Q&A tab. So most people are familiar with Zoom nowadays. If you look at the bottom of the Zoom app, you will see that there's a Q&A option or Q&A tab. And if you click on there, you should be able to post questions. So if you've got any questions, please feel free to post the questions there, and we will get to those questions at the end if there's time. Now, without any more delays, what we'll do is we'll just quickly switch the screens sharing to Michel. So if you just give us a second, we'll hand over to him. Right, you should be able to start your screen sharing now. Cool. I think you're muted, so there we go. Perfect.
Yeah. Good day to everyone. My name is Michel Schildmeijer. I'm from the Netherlands, from Amsterdam. It's 6 a.m. in the morning for me. I don't know where you all are located, but yeah, well, hope you enjoy my session. So first of all, I already told you I'm from Amsterdam. I'm from the Netherlands. I'm working for a company named Quality. I'm an Oracle Ace since 2012, and since 2019, I became Oracle Ace Director. I authored 2 books about WebLogic, and I started my IT career back way in the 90s already. And the talk of the day is about containerization, and special also the role of Oracle and what Oracle does in this space. And I want to discuss around the alternative ways of building a container platform other than with the familiar Docker Defacto standard tools. So the topics for today are containers and trends, container runtimes, the security around containers, because that's a very important issue and topic. I want to tell you about the integration of this new way of working with containers, and also like to discuss the alternative tools for building and running and browsing your container images and inspecting them. So first of all, you can see everywhere where you look, if you talk about infrastructure or building applications, the new discussions are how am I going to build my infrastructure around these containers, and also around all the new technologies regarding microservices and serverless technologies. So since the rise of cloud and DevOps, you can see infrastructure has made a major transition in how to build, to provision and operate a live production container platform serving the 24/7 needs, high demands, and new, better, and functionality, performance, scalability. All those issues are very important. So transitioning an existing infrastructure to a container-based landscape, this is something it has to evolve within an organization, and it's not an easy task to do. So one has to think of implementing all the benefits of this new way of working, and keep in mind that things like security and maintainability are also important, separate from productivity. So if you look at this prediction of Gartner, they predicted in 2019 that at that very moment, only less than 30% of the organizations were running some kind of containerization in production, and they predict that in 2022 it will be almost 75%. Now we don't know if the prediction comes out, but you can see the trend of moving from traditional infrastructure to containerization, especially when you're in the cloud and you're developing more cloud native applications, but also the companies that provide a managed cloud platform, they also are going to shift to containers instead of the traditional server infrastructure. So if you look at these 6 areas of which are hot in that container native landscape, then you can see the orchestration of containers, container lifecycle management, networking, storage, and monitoring are very important. But number one is security. So security is really important to discuss, and this is also a thing which I would like to discuss in the next slides. But first of all, let us see what containers are and how they evolved into what they are today. So actually there are 3 major transitions to identify in this thing. The bare metal servers, the virtual machines, and in the end, the container engines. So if you look at virtual machines, first of all, the server hardware, bare metal server. When you look at that, then you have a piece of hardware in your data center, maybe 1 or 2 or 10 servers, depends on how much resources you need. You install there an operating system, and on top of that, you have an application running, or you have a database running, or several databases running, high availability or not. But the next step for that is, as anyone would know, virtual machines. There you have your virtual machine, your operating system of your hardware, and on top of that you have an extra layer, a driver software, sort of driver software, which is called a hypervisor, and this hypervisor can translate a guest operating system of the virtual machine to the initial hardware where it's running. So before containers gained popularity, a prior approach of this was this virtual machine thing. And if you look at one physical server was able to have multiple applications through this virtualization technology, they were running isolated with their own operating system, and it's still being applied by a lot of companies to use some kind of virtualization technology. And in this case, the physical server runs several virtual machines, each with its own operating system, using a simple hypervisor layer to on top. And you can run several operating systems by this way of working simultaneously. And there's a lot of overhead on the servers because resources get used depending on the number of virtual machines. So you can limit it only to depending on the resources you have. So in contrast with container technology, the server runs as a single operating system, and each virtual machine is able to share this single operating system with others, but it's still an isolated part. So when you look at containers, it's really a buzzword maybe because everyone talks about containers in cloud native communities and cloud native developments. But really, what are containers? It's a understanding which you can explain in many different ways. But in fact, a container is when you look at it at the most deep level, it's a small set of services and applications which are one package running somewhere on a server using some kind of container runtime software. And some of the key aspects of containers are that they don't share the operating system kernel. They share the operating system kernel, sorry. They don't have any hypervisor in between. You can isolate resources like storage network, CPU, memory, and it's packaged in an image and it runs as a process, or if you look at orchestration, multiple processes somewhere on a server or a bunch of servers. And containers make use of containers started actually initially on a Unix-based platform and Linux. So there are now initiatives also to run containers on Windows, but the initial technology was started on a Unix-based platform. So I already told you they make use of namespaces, Linux namespaces, Linux profiles, security profiles, C groups, CH roots to provide an isolated environment. So in addition, containers can run different Linux distributions from its host operating system, and you can use the same CPU architecture, but it's you can run any application technology you prefer if you prefer that more than the other. So container technology does not only contain the software, but also the dependency, including libraries, binaries, but just as enough as it should be. So no overhead in your container. So that makes it possible to run a container very lightweighted. You can download an image and build your container, download an operating system image, strict version, include your application and libraries and binaries, and run this container with any container software with a blink of an eye after you build your container. So if you look at this diagram, then you can see the main differences. When you have a virtual machine, you have your hardware server somewhere running. You have your core operating system. You have your virtual machine engine, the hypervisor, and on top of that, you have your guest operating system running the operating system and the application binaries, libraries, and the application itself. And when you look at the right here, you can see your container technology, the server hardware, the core operating system, and on top of that, some kind of a container engine and running processes which are in fact runtime representatives of container images. So if you look at a little bit about the ancient container stack, that you can see containers already is something which is not new. It was already there since the first commercial version of Unix was released in the end of the 1997 it was. And at that time, you already had some kind of way of isolating resources, isolating processes with specific resources of your server hardware. And the base of all the container technologies, in fact, CH roots. And this concept was already there, beginning with the starting of Unix. And it's like an operating system call for changing your root directory for a process and its children to a new location on the file system, which was only isolated for that particular process, an isolated disk space for each process, and isolated CPU time for your process. And this was later added to the BSD version of Unix. And some other technologies which evolved more and more in the years, and you could see like Linux containers, which were the very first mature container already. It was a complete implementation of the Linux Container Manager at the time, and implemented using C groups and Linux namespaces. And it was delivered by a liblxc library on provided languages for binding the APIs written in for Python and some other languages like Go and Ruby. In contrast to other technologies, it works with a vanilla kernel without requiring any patches. So this was around 2008 when this was started and run. And through the years, Docker became more the de facto standard for running containers and building containers with the software of Docker. And you have the CE version of Docker, which is an open source, and also the enterprise, which was acquired by Mirantis lately. So Docker, in fact, was for a long time the standard for running containers, but there were some issues which were identified. And if you remember one of my first slides, security was one of the issues, and is one of the issues, and the most important topic in container landscape. So when you look at traditional container application architecture and how a DevOps team or a team which are building applications and container infrastructure, then you can see several stages where you can have some risks. So first of all, you have your developers. Your developers are building, they are testing their applications within container images, and they push it to some registry. It can be an internal or it can be an external registry. So at that point, you can already have a risk. So you can have an image risk because images are effectively static archive files that include all components used to run a given app. Components within an image can maybe missing critical security updates because it's stored in an image. So you need to take care of all your security vulnerabilities and address them with the security updates you get from your provider, your software provider, or which are known from the community. So you have to be aware of that. So an image created with fully updated components may be free of known vulnerabilities for days or weeks after its creation, but after a while, sometimes you get some new vulnerabilities known, and you have to be aware of updating your images in this case. But you also have other stuff like packaged malware, or do unencrypted text files with passwords including in it. So you have to be aware that image risks during the build, test, and push stage are to be identified. Next one is when pushing it to a registry can be also a security issue. So a registry risk is also there looking at you. And well, images are often created with, already told you, sensitive components like maybe unencrypted passwords, but also organization proprietary software, embedded secrets, confidentiality risks, data transmitted, like the transmission of an image to a registry can be security risky, because you can have some kind of interception in your network traffic when you push your image to a registry. Some hacker or organization can be in the middle of it, the man in the middle of the attack, which is called it, and it can steal your network traffic in between, especially when you push it to an external registry, like a public registry, for instance. And it can be an exposure for your container images, which may contain very sensitive data. Another thing is that when you have your images in registry resided, they can become stale because you deploy your push your image to a registry, and already told they can be out-of-date versions of the software which you built. So you have to be aware of this lifecycle management of the software, not to have vulnerability in your version. So that's also a risk of your container landscape. And another one is restriction of authorization. When a developer builds an image, then maybe there is not enough fine-grained security in it built in it, so everyone has access to everything. So you also need to be aware of that your images are have the proper security policies applied within it. So the next one is the orchestrator risks. The containers these days need to be managed, and that can be a risk as well, because still you have this unbounded orchestrator risk when a team builds a Kubernetes cluster and you have access to any resource in that cluster. That can be a risk. When historically, when Kubernetes or an orchestrated platform was installed and configured, it was designed with the assumption that all the users could interact with the container landscape, but that seemed to be not the most secure way of how to do this, because you have different sensitivity levels. You have mixed workloads in your containers running, like finance data and human resource data. They're all in the same, so you need to be aware of doing some proper isolation between those different workloads, so they don't compromise within your landscape. And the last but not least, and this is the one which I want to discuss with you, the host operating system risk. In the end, somewhere this container is running on server hardware using this container runtime software, and on this server hardware you have a large attack surface, because every host can be attacked by a hacker, and if a hacker comes in, then the hacker can exploit across the entire host where all your containers are running. It can be maybe 10 or maybe 100 with all kinds of application sensitive data. A hacker can attack your operating system on the server level, so that is a very risky thing to have. So you have to address this and be aware of that. All the containers are running, are sharing some components, and they are also vulnerable for what is for attacks. So the concept of sharing kernel, which Docker especially has, is a security risk. So these are more or less all the vulnerabilities which you can think of in this thing. And one of the examples of such a attack was initiated a few years ago with a KillChain attack on a Docker on Docker containers, which were pulled out of the public Docker hub, and this was using some malware. Malware was built in these containers, and these containers were functioning as a crypto miner without knowing of the initial of the customer which was using it. So when you look at this this way of working, there was a malicious Docker or GitHub account where images were pulled. In fact, the images were infected with this crypto mining hardware, and then it was pulled by the organization. And when you look at a typical KillChain, then you can see there are several steps within it, like the lateral movement, and first of all weakness discovery, then lateral movement, and in the end the infiltration and running malicious commands in your containers. Right, these was already discussed. This is really the issue on the host operating system level, the shared kernel risk. And through the years, with the evolution of containers from the open source community, there was a need of more isolation, but still have the lightweighted of container, the lightweighted thing of what a container can do. So this is the typical application containers. You can see the host operating system, the kernel running system process with namespaces. This is of course already some sort of isolation, but they still share this large attack surface by make use of the same kernel as the other process. And when you look at some alternatives nowadays, Kata containers are an alternative for Docker-based containers, and Kata containers are in fact still the same as a Docker container, but within it, its own kernel. So it's an isolated kernel space in the container itself, but still there's the lightweighted characteristics of traditional Docker containers. So if you look at the alternatives of container technology stack, it's not only the container itself, but also the runtime of containers, the build of containers, and pushing and pulling it and inspecting it in your registry. And this is an overview of what you can do to replace your current tool set of building and running containers. So Docker, the Docker daemon can be replaced by Cri-o or containerd. The runtime can be replaced by Kata containers. Your CLI, so your way of managing your Docker containers, can be replaced by Podman. Building your Docker containers can be replaced either by Podman or Buildah, or and last but not least, Skopeo can be used to scan through your image registry to your containers. So when you look at these new technologies, they all support the Open Container Initiative, which is an open source initiative of building and standardization of containers and container native landscapes. And when you look at orchestrators like Kubernetes, it also fits in, and it also is optimized for running in the Kubernetes runtime. So a technology like Cri-o is OCI based, and it's compatible, fully compatible with the container runtime interface of Kubernetes. So it's specially designed for Kubernetes, where Docker, when Docker was there, Kubernetes wasn't even production. It was maybe at the Google board level from Google, but Docker was already there. So after that, they merged and were adjusted for running in Kubernetes. But Cri-o, for instance, is specially designed for Kubernetes. So when you look at container runtimes run in a sort of isolated process, and this process is comprised component is called shim, and shim is a launching runtime for handling containers and also container output and container errors, and it reports the status of your containers back to the orchestrator. So these things are used for Docker containers, but also for new Kata containers. So they, when you look at containers and new container runtimes and Docker can be integrated seamlessly with the new container technology. So you don't need to rebuild your entire environment to run new container technologies with your existing Docker ones. So this is a traditional Docker way of working, using the standard shim version and the Docker engine on top of that, maybe with containerd. But when you look at Kata containers, you have a new version of shim. That's the thing which has changed, but you can still use your Docker engine and containerd to run Kata containers. So if you look at Kata containers, then the technology which is lying underneath it, then it's a bit different of what Docker containers run on. So I already told you about hypervisors. You have your traditional hypervisors like Zen and VMware and Hyper-V. The traditional hypervisors from VMware and also Oracle hypervisors, they are so-called type 1 hypervisors, and they can run directly on your hardware, on your bare metal, with no operating system underneath it. Kata containers also use some kind of a hypervisor, and this hypervisor is called KVM. KVM is the one Oracle supports now these days, and Oracle was also always supporting Oracle VM, but Oracle moved away from that and sets hypervisor as the main hypervisor for its operating system, Oracle Linux. But apart of that, you also need some kind of an emulation in between to emulate your virtual machine in your container. And some of the most well-known and de facto standard emulation software is QEMU, and QEMU can be used with KVM, and another one's Firecracker. And Firecracker is used on Amazon micro virtual machines, where you can pack thousands of micro VMs onto the same machine, and it means that every function, container, or container group can be encapsulated with a virtual machine barrier, and they can enable workloads for different customers to run on the same machine. But that's on Firecracker, and Firecracker is in fact an alternative for QEMU, but it also makes use of KVM. But when you look at Oracle, Oracle supports QEMU, and already told you it's an emulator for your virtual machines, and it works with KVM and also the Zen hypervisor, so you can do it multiple ways. When you look at your Kata container architecture, then you can see your Kubernetes cluster at the left. You have your container runtime and your shim for input and output, and your runtime for the OCI commands and specs. It's not OCI from Oracle Container Infrastructure, but already told you, Open Container Initiative. And in between, the communication protocol is gRPC, and in between there's a Kata proxy. And when you look at Kata virtual machine, the Kata container, then you have inside a Kata agent running, and the hypervisor of the container, and on deepest level, your container namespace with all your container commands and executables. One of the prerequisites to use your Kata containers is that you have to set some CPU flags. You have to have set the virtualization on your CPU level. So you have to check on your CPU if it's enabled by this flag. So already told you, Oracle supports Kata containers fully, so you can build your Kubernetes cluster if you're a managed Kubernetes provider and you want to build your managed Kubernetes server on Oracle Cloud Infrastructure. Then it's fully supported and fully available for your Oracle Linux. And also Oracle Cloud supports the additional tool sets like Podman, Buildah, and Skopeo, which we'll come to later. Looking at the Kata Cri-o integration, then you need to do some stuff. You need to install some things like the QEMU package. You need to have the proper image to install. You have to connect to the proper YAM repositories and channels, and you have to enable some stuff. You have to install your kata-runtime. You have to enable some kata dependencies. So that's more important too. And if you run Docker, I already told you it can be seamlessly integrated with Docker. You can tell Docker that you could have to use the runtime startup. The Docker service can be integrated with the Kata container, so you can tell Docker to tell startup the Kata container, the Kata runtime as the default. And you also need to tell the Docker daemon to use the native C group driver systemd instead of the C groups FS, which is in fact a deprecated version. So you need to have to tell the Docker daemon to use systemd as the C group driver. And you can install the CRI-CTL, which is a command line interface for Kata runtime, but also for other CRI compatible container runtimes to test your containers. But Cri-o can do more for you than CRI-CTL. So if you installed all these things, then you need to integrate your Kubernetes with the new container runtimes. First of all, I'd like to discuss a few of the Kubernetes basics. Maybe if you already into Kubernetes, you already know what these are. But when you look at Kubernetes and its risks, the orchestrator risks, which I already told about in some slides ago, then on certain levels, there can be some risks looking at you. Sorry. First of all, when you look at Kubernetes basics, then you have your master, your master, which controls the Kubernetes nodes and hosts all the API interfaces. And you can have a single master or maybe multiple masters if you do high available. You have your nodes, which in fact are running all your application containers. Then you have your pods, and pods is in fact the container representation of Kubernetes, and it's in fact a scheduler entity for a group of containers. So a pod can run a container or multiple containers, sidecar containers within it, to run your application. Then you have your application controller, where you can run identical pods across a Kubernetes cluster. You have your communication interface, your service, and you have on every node you have a Kubelet running, which is in fact manage your container lifecycle on all your Kubernetes nodes. You have your kubectl for command line tool for your Kubernetes managing, and etcd, which is a key value store for all your cluster configuration. So when you look at this diagram of a typical container Kubernetes cluster, then you have several components which I've discussed previous. And first of all is the risk of access to your nodes. This can be a security risk, because when you have your large I talked about these large attack servers, when a hacker or an organization has access to your nodes, it can access everything, almost everything they like. So also access to the other nodes through maybe your control plane access to your daemons. So all the daemons which are running for Kubernetes can be at risk at the moment. Your container runtime, already told you about that. And access to the Kubelet can be also a risk. So manipulating your container runtimes from Kubernetes perspective by manipulating your Kubelet. So if you look at the traditional integration of containers running with Docker, then you have your Docker daemon, and Docker daemon uses runC as the container runtime. You have your container image, and the Docker daemon is integrated with your Kubelet to tell the Kubernetes about the container lifecycles. And when you look at, you can also use containerd, by the way, instead of Dockerd. And you can use Cri-o instead of Dockerd. And Cri-o is also daemon-based, but still it's more lightweighted than Docker. And but you can also run Kata containers instead of Dockerd. So you can replace your Docker daemon fully with Cri-o and Kata containers, or using containerd. The way I'm telling it like this might be confusing, but these are all initiatives from the Cloud Native Computing Foundation, all open source initiatives for running containers. So there are multiple possibilities for running. You can run Dockerd with runC or with containerd. You can run Dockerd with Cri-o. It can all be mixed and merged. So that's why it seems a bit confusing. But these are all the possibilities for Kubernetes to run with container runtimes. So when you install Kata containers in Kubernetes, then you have to, it can be done on a running cluster. So you don't have to build a new cluster. You can migrate it. You can drain the Kubernetes master. You can instruct the kubelet to run the proper container runtime and drain the worker nodes and and migrate to a new container runtime. So these are some of the steps. I can see my time is already almost up, so I will make a quick, make it more quick. You need to tell the kubelet service to make use of another container runtime, in this case Cri-o, and you can join the cluster again by using the proper Cri-o container runtime interface socket. In this case, it was containerd, but you can also use the Cri-o configuration. Depends on what you prefer. And then you can run your Kubernetes cluster with also different container runtimes. Here you can see some of them are running container runtime with Cri-o, and some of them are using containerd. Maybe you want to migrate from Docker container runtime to Cri-o. Then you can say, well, I take one node and run it with Dockerd, and one node I run with Cri-o. And here you can already told Dockerd can use kata runtime. So enable your pods and your deployments with Kata. You have to make use of the runtime class to say to the pod or to the deployment that it should run the Kata and the QEMU hypervisor. So you have to label your deployments using this runtime class. And this is an example. First of all, you can label your containers to set it to true for your Kata runtime. Can be 1 or maybe 2 or maybe 5, depends on how many nodes you are, or all, can be all as well. And you can also say place a taint on your Kubernetes master node to not run any application container on it. And if you have a deployment of an application, in this case it's a Apache PHP, then you can label it with the runtime class. And then if you start up a container, then you can go to the specific node and see that the QEMU is running for that specific container. So that proves that your container is running the emulation software and it's running Kata containers. So this is a short demo, but I don't think I have the time for that to run it, because I also want to talk briefly about the other tools. You have your container images, and you have several other tools for building it. If you want to build containers, the best tool you can use is Buildah. If you want to run containers, the best tool to run is Podman. And if you want to tag images of your containers and inspect them in your registry, then you can use a Skopeo and transfer them to your registry. And one of the major the most important things of these tools are that they are more secure and they're all daemonless, so you don't need to run it as a daemon. So it only starts a process when you do a call to it. And another benefit of it that you can use it as a non-root, like Docker, you have to run as root, but Podman and Skopeo and Buildah can be run as a non-root. So that's a major security improvement. And when you look at Buildah, Buildah is in fact an extension of Podman. You can use Podman for building your containers, but Buildah is more sophisticated, more fine-grained to build your containers. So you can do Podman build, but I prefer to use Buildah because you can have more options. By the way, every Docker file is fully compatible with these tools, so you don't need to change anything of your Docker files. And if you have a lot of Docker commands in your scripts, in your shell scripts, then you can replace them using Buildah or Podman, but you can also make aliases on your operating system, so they will point to your Docker executables, but under the hood they are still the Buildah and Podman executables. And Skopeo, already told you, can browse and manage your image registries. So I don't know how much time is left. I wonder if there are any questions at the moment.
Yeah, just quickly jumping. There's probably you've got a couple of minutes or so. Okay. On the questions, I actually have a question. This is a fascinating, amazing presentation. Really enjoying it.
Thank you.
The Buildah utilities and Podman, are they easily available on the Linux distributions, or are they quite specific to Linux distributions?
Well, first of all, you can download them, but you can also with Yum from the Oracle Linux Yum repository, they're fully available, so you can download them using a Yum package manager. If you're using Ubuntu, you can use the specific from there. So they are available through all the well-known repositories.
Oh, perfect.
Yeah. Okay.
Oh, thank you so much.
Yeah.
Just for the attendees, if there's any questions, you're welcome to put in the Q&A box. I don't think there's any questions at this stage.
No.
Cool. Anything else you would like to finish off with? It sounded like you wanted to just show something or do something.
Yeah, I can show you a short how it works. Let me share my other screen. So these are all Oracle Linux. I have 3 nodes in my cluster. This is 1, 2, and 3, which are running in the Oracle Cloud Infrastructure, by the way, using Oracle Linux. And what I wanted to show is to run an Oracle database on Kata and an Oracle database on non-Kata. I have prepared 2 YAMLs, one with the non-Kata and one with the Kata. So when I look at the YAML file, I talked about the runtime class. Let's see where it is. Here it is. You can see I told the deployment that when to deploy this Oracle database, you need to have need to use the Kata QEMU class. So that means when a container is started in a pod, then it will call the QEMU interface in KVM hypervisor. So first of all, I will do the none one. I've created a namespace. So there's nothing in it because I didn't apply anything. So I applied, first of all, the deployment without the Kata interface. So if I now do get pods to identify where the pod is running, then you can see it's running on the Kata 2. And Kata 2 is labeled as a non-Kata runtime, because if I do if I show the labels of the nodes, then I identify this one as non-kata, so it will run over there. It's still in the starting phase. And within the container started, but the database within it is not started yet because it needs to initialize all kinds of install scripts to run the Oracle database. So if I now apply the other one with the kata, which should be running then on this one, because this is labeled as true. I'll apply the kata one. So you can see it's placed in here, and then if you here I want to see if the Kata container is really started making use of the QEMU software. There you can see it's running in here. Let's see if the database in here already has started. No, it's not started. But this proves, in fact, that you can run either Kata containers on a node when you label the node as kata-runtime, and also make use of the kata-runtime class, or do it without if you are maybe in a migration situation. So that is what I wanted to show you. So that's about it. That's my presentation. Thank you very much.
Cool. Thank you so much. That was really enjoyable. I really enjoyed that session. I use Docker every day, so it's really, really great session. Thank you so much.
Okay.
And thank you so much for everybody attending the session. If you've got any questions, you're welcome to interact with Michel via the speaker page. So if you go to the session page, you'll be able to post questions and comments there. Anyway, and there's also a lot of other sessions running, so please feel free to register to some of the other great sessions that's running over the next few days. And I hope you enjoy the rest of the conference. Thank you so much.